start it for now at least. Two of you are not here anymore. Anybody have any questions? Right. So if you do not have questions, I am under the assumption that you understood everything, right? Right. So let me then go into this second, the test about the precision of the perihelion of Mercury. And remember that we have talked this before as well. Now Newton predicted that path of an isolated planet move in an elliptical orbit. So that is in general, all these planets that that belongs to our solar system. Okay, Nirmal, this pattern is actually 2D and not 3D, right? So it's only a theta equal 5/2 plane. In the plane, it rotates. That's what happens. Well, that's a good question. So that because we have assumed that theta equal 5/2, which means we are limited our motion to a certain plane, right? So this moves in only on 2D plane. Now, one of the very nice applications in this general relativity is actually when you look at these general elliptical orbits, this is how a planet moves around the sun. And this we have discussed this earlier, but just to remind you, the sun is right here at the one of the centers in the ellipse, and then here is the planet moving in an elliptical path, and the length of the semi-major axis is given as A, and this is the semi-minor axis, so that is B, and this point right here, which is the closest point for the sun, is called as the perihelion, right? And for this planet Mercury is, as you know, that's the closest planet to the sun. What we have observed is, instead of moving in a general elliptical orbit, this perihelion, so that is the closest point of the planet to the sun when it moves in an elliptical orbit, perihelion of the Mercury seems to advance very slowly in the space, right? This perihelion point seems to be changed very slowly in the space, right? And this phenomena is known as precession of the perihelion. And this is something that astronomers have observed, right? And we have not observed an effective or a large amount of precision like this for other planets, but this is very specific for Mercury. And from the knowledge now you have with this general relativity and the Schwarzschild space-time that we talked up to now, straight away you should get the point now that this is very close to the sun, and sun is this massive object, and because of that, as the Schwarzschild metric described, the space around the sun should be curved, it should not be a flat space, and this curvature has led to this advance of the perihelion, which we called as the precession of the perihelion, right? Now, what actually happens is, here is the sun, and Mercury is going around, and this perihelion position is changing with the time, and which will, if you once the perihelion is changing, when you draw these elliptical ellipses, you can see that this starts to create a pattern which is very similar to this pattern right here, which we described as a result of this extra term right here, right? Now you can understand what actually has happened. Actually, a large, so there is a spelling mistake, right? A large part of this precision is due to gravitational effects on Mercury due to the presence of other planets, right? Now, that is something important for you as well. Now, this precision happens not purely because of the effects coming from this curved space that we described from the general relativity. What actually a part of this precision is due to the fact that you have other planets that are close by apart from the sun, right? So those planets also, affect or apply some gravitational forces to these planets, because we cannot avoid that now. And because of that, there should be some precision for this perihelion point, right? Now, but the problem is, even you take that into account, there is a small movement of 43 arc seconds per century that could not accounted by any non-Newtonian force. You can calculate these effects from the other planets and check whether this perihelion of precision can be explained. But what has happened was, still even you account or take those calculations, there is a small portion like 43 arc seconds per century that we could not uh, explain, right, from these effects from the other planets. Now, in 1915, Einstein used an approximate form of the Schwarzschild metric that we discussed above to predict the precision of the perihelion of the Mercury, and the additional term in the orbit equation 43. So that is actually in effective potential, this is the term. And if you go to the orbit equation 43, this additional term right here is the one that is responsible for this small precision. That part comes into play here. Right, the additional term in the orbit equation 43 is the one which is responsible for making this advancement of the perihelion. So that comes from that small term, right? Now, from some calculations, which we are not going to do in this our lessons, so I also do not expect you to prove that as well. But if you do some calculations, we can prove that because of that small additional term that is in the orbital equation number 43, we can actually derive this equation, which tells you the change in the angle delta phi, that should be equal to 65 gm over a times 1 minus e squared times c squared. And I guess all of you know these terms now, right? Mass is the total mass. Now, in this case, if you are going to look at the precision of the Mercury, this m should be the mass of the sun, or the sun is the massive object that curves the space there. And a is the semi-major axis length, e is the eccentricity. Don't get confused with this E with the previous E that we discussed. It is just a constant that we talk. Now here E is the eccentricity, and those are the three terms actually that appears in this equation. And using this equation, you can calculate the precision angle delta phi, right? And this is derived from those equations that we earlier discussed, but we are not going to the derivation. But I want you to prove that how nicely these observations and the theoretical results match at the end. Now, if you do the calculation, before that, let me discuss this point as well. Delta phi becomes larger as E goes to 1 and A goes to 0. And the idea is, if eccentricity is larger, or eccentricity go into a value of 1, and then also A is the semi-major axis length. When it becomes smaller, this value will become larger. Right? That makes sense now, because if the semi-major axis length is smaller, so that means the Mercury we should be very close to the Sun, right? And orbit of Mercury has a high eccentricity. So that is another factor. When you measure the eccentricity of these ellipses, orbit of the Mercury has a very high eccentricity and a smaller semi-major axis length, right? So which makes this mistake here, so that I will. So which makes it a good candidate, right? Now I have a question for you. Mercury has a period, so I have given the period of the Mercury 87.969 days, and then the semi-major axis length is 5.791 times 10 to the power 10 meter, and the eccentricity of the Mercury is 0.2067, and the mass of the Sun is given as well. What you need to find is a delta phi value, right? Position of the Mercury. So let me leave that question for you, and so I think I have not clearly stated what you need to find. So let me just make this question a little bit clear for you. I treat this way. Calculate the portion. So right, so what you need to find is calculate the general relativistic portion of the Mercury's perihelion advance, and you have to express your answers in arc seconds, seconds of arc per century or arc seconds per century, right? So it shouldn't be that problem for you. So try yourself. So I will post this note, and so what I am actually doing is these will appear in your next tutorial, but I am giving you the questions ahead of time so that you know where you should how you should calculate it now, right? So you can finish the question, but I will collect all these things to a tutorial later, but you can do it even now and keep your answers, right? Right, so that is one of the tests that we should look at in general theory of relativity, and this is actually a nice proof and a nice example to tell that this general theory of relativity works, right? And once you calculate this, you will get a very accurate result that is very close to 43 arc seconds, right? So that is the number of arc seconds exactly that we could not explain using the normal Newtonian theory. So it should be important. And you can use this equation and just try to find the delta phi, and you may need to do some unit conversions for this as well, right? So that is the second test for the general theory of relativity. And the third test is gravitational deflection of light. And this is again due to the curvature of the space-time. Einstein expected that the deflection of the light by a massive body, and as you know that because when you have a massive body, the curvature, the space will be curved around that, and because of that, Einstein also expected that there will be a deflection of the light by these massive bodies due to the curvature of the space-time, right? Now, what he was expecting is that for the light rays passing the limb of the sun, an effect large enough to be detectable is expected. It is something like this. Now, for our solar system, sun is a very massive object, and what he would expect is when there is a when there are light rays passing the limb of the sun, so that means this outer area, he expect the light rays would curve like this, right? And as a result of this, what would happen is, now you have the sun right here. If the light rays are curved like this, when it comes to your telescope, you would the actual position of a star would be right here, but you would see that it's like the light rays looks like come from here. So your apparent position of the star will be here, right? So this is something that Einstein expected from his theory due to the curvature of the space-time around these very messy bodies, right? Even though we are not going to prove this mathematically, we are going to check whether this is correct or not, right? So this is deflection of the light of the curvature due to the curvature of space-time. So it should be done. Right. Now, once again, using that earlier equations that we learned for the Schwarzschild space time, one should be able to prove this amount of deflection as well. Again, we are not going to prove the equation, but we are going to use the equation for the calculations. Right? Light rays that passes close to the spherically symmetric body of mass m, the angle of deflection, that is delta theta, is predicted by this particular equation according to the Einstein's general theory of relativity. So as I told you, we are not going to prove this equation. We are going to use it. And B is called the impact parameter. So that is, in other words, perpendicular distance from the deflection body of the initial path of light ray. And also you need to note that this equation is derived by using one of the Schwarzschild geodesic equations and limiting the motion to theta equal phi over 2 plane. Right? So I just have mentioned here uh, how we derived it, because we are not going to prove it, right? So what we can get an idea how we derived it. Now, using this equation, I again have a problem here for you. Calculate the angle of deflection of the ray of light in arc seconds, just casing the sun, right? So you need to use this equation again to do this calculation. And I have given you the data needed, radius of the sun and the mass of the sun, gravitational constant G, right? Now, let's say you do the calculation, it's okay. And how do you observe this? Right? So you assume that there is the sun is right here, and the actual position of the star is here. Once you look at this star through a telescope, you should see it here. Now, the problem is, how do you observe this one? Right? Now, if you, probably this is sometimes even in newspaper articles as well. So there was one astronomer, I guess his name was Eddington, if I remember it. Yes, it's called one of the British astrophysicists called Arthur Eddington observed a total solar eclipse and tested the general relativity. Now, can anybody tell me why you should test this when you have a total solar eclipse? Why you cannot test this even another day? What is this specific thing about it? You probably have heard this before as well, that this deflection of the light due to the appearance of the sun is tested when you have a total solar eclipse. And in 1919, this British astrophysicist called Arthur Eddington, he used to test this Einstein's idea about the deflection of light when they have a total solar eclipse. Right? Why astronomers waited for a total solar eclipse to test this? So that you go out tomorrow and test this, this deflection of light due to the sun. Why you cannot test it in that way? Anybody have any answers? You should know the answer, right? This is, very simple answer that you can do it for this. Nobody knows why you cannot. For example, let's say you have a telescope, right? You go out tomorrow to test whether this Einstein's general theory of relativity is correct. So Einstein has assumed that the deflection, due to the deflection of the light close to the limb of the sun, you should the light should be curved, and because of that, you will see the apparent position of a star that is just behind the sun is a little bit different than the actual position, right? Why you should wait until total solar eclipse? Why you cannot do it in the general day? Everybody knows the answer. There is a very simple answer for this one. Can you observe stars at daytime? You cannot, right? At daytime, you cannot observe any stars because of this the glare and the amount of light produced by the sun. Right? And I mean, this is the reason. Once you have a total solar eclipse, what happens is this the light coming from the sun will be completely covered on that day, so that you can see the surrounding. Right? And this is why they have chosen a day where you have a total solar eclipse, where the sun is completely covered, so that look at and observe this particular phenomena. Right? So that is the only reason. So in 1919, so the above prediction is, possible to observe during a total solar eclipse, and I told you why you observe it on a day where you have a total solar eclipse. In 1919, a British astrophysicist called Arthur Eddington, so he observed a total solar eclipse and tested the general relativity, right? Should be. So he's and he confirmed that the starlight was deflected as predicted by the general relativity, and this was considered as the third test for the third test to prove that the general theory of relativity is correct, right? One of the one of the memorable tests for actually Einstein at that time. And then let's look at the fourth one, gravitational time delay of signals passing the sun. And this is called Shapiro time delay for a reason. And right, I guess this is the last, yes. So this is the last section. Right, I guess probably this is a good point to stop now. It's already 7:25, so I will try to stop right here now. Anybody have any questions up to here? Right, if not, just remember what we have actually talking now for a few days, starting in, so we started talking, remember that we derived or we kind of discussed about the Einstein's field equations, and after that we came into this topic called Schwarzschild metric, where a metric that defines the space around a massive object, and then we have the Schwarzschild metric in this way, and then we discuss different forms of the Schwarzschild metric in the last few days, and then actually we derived the Schwarzschild metric, and I showed you how to derive the Schwarzschild metric using the vacuum field equation. And during the proof, I showed you one or two, you know, how to find these connection coefficients and those kind of things. And I ask you to calculate these connection coefficients, and then the Ricci tensor and the Riemann tensor. And from that, actually, you could confirm that these coefficients are correct for the Schwarzschild metric. Right? The important thing is once you know the Schwarzschild metric, and then we actually discuss some of the effects of the Schwarzschild space-time, and some of those are, one is called, so we define the Schwarzschild radius, by the way, and then from that, we actually discuss some of the coordinates and physical singularities we have, and then gravitational, about the gravitational time dilation, and then gravitational redshift, and all these comes as a result of, you know, curvature of the space around these massive objects, which is described using this Schwarzschild metric, right? And we derived gravitational time delay and gravitational redshift. And these simple derivations, I expect that all of you should be able to do, right? Because these are like some of the simplest derivations that you can do using given the Schwarzschild metric, right? You don't need to remember it. And then I talk you the difference of the proper distance, and then between the proper distance, the relationship between the proper distance and the coordinate distance using this embedded diagram. Basically, the d sigma is the proper distance, where dr is the coordinate distance, and we discuss the relation between those two, and also I discuss with you an example what happens as a result of, you know, with this proper distance. And then today we started discussing about the geodesics of the Schwarzschild space-time, which tells you, so I started by different form of the Schwarzschild the geodesic equation, and then I derived the conserved quantities. In fact, two main conserved quantities depending on the nature of the Schwarzschild metric, and then we used the four velocity relation in special theory of relativity, and derived and adapt it here for the curved space-time using the metric tensor G mu nu. And then from that, we derived using the conserved quantities, and also this relationship about the four velocity relation we have derived the radial motion equation. And then we use some of these, substitutions for the that we derived as conserved quantities, and from that we got an equation for the energy, and also then derived the orbital motion aspect, right? And from that we discussed that there is an additional term compared to the Newtonian physics in this orbital equation. That additional term is the one that is responsible for make these differences between the Newtonian physics and this and the Schwarzschild space-time, right? And also I discussed with you about the effective potential term that we also derived in the classical mechanics, and due to the difference of the effective potential, you can see that for any positive angular momentum, given an angular momentum in Newtonian physics, you cannot go into R equals 0 value, right? So that is why these things are in an orbit. But under certain conditions, this could happen for the Schwarzschild space-time. One can go into R equals 0 if it pass this unstable position, right? And that we discussed. And also as a result of this extra term, even though we did not derive formally, we discussed that as a result of this extra term, this the precision of the perihelion, which means the orbits will have this nice pattern, right? As a result of that extra term that comes from the Schwarzschild space-time, from that metric. And then we applied that knowledge to discuss about the second test of general relativity, that is about the precision of the perihelion of the Mercury. So what that means is this perihelion position, which is the closest position to the Sun in an elliptical orbit, this perihelion used to advance with the time, right? So it normally makes a pattern like this. And this advancement is due to two factors. One factor is due to the gravitational effect from the other planets, and there is a small amount that even you cannot explain from the gravitational effect from the other planets. Now that comes as a result of the curvature of the space-time due to the Sun, right? And that amount can be calculated using this Schwarzschild metric, and by deriving this particular equation. And we did not derive it, but we discussed it, how you can derive it. And then using this equation, I asked you to plug the numbers and try to calculate how many arc seconds per century that this the value of this advancement, right? And once you calculate it, you will get exactly a value very close to 43 arc seconds per century. It is a very small value. And then at last, we discuss about gravitational deflection of light, which is also predicted by the Einstein's theory of relativity. And we discuss here because of the massive objects such as Sun, the light rays will be deflect slightly due to the curvature of the space close to the Sun. And because of that, the apparent position of the star will change, as you see right here, than the actual position. And this is tested by one of the famous astrophysicists called Arthur Eddington in 1919 during a total solar eclipse, because that is the time that the Sun is fully covered, that we can look at the surrounding object and stars. And for that also there is a different Schwarzschild equation that we can have to use, and then derive this angle of deflection. And once again, we did not prove it, but I have given you the equation that you can use. Using this, you can do the calculation and find the angle of deflection. And I have assigned that also for you as an exercise. And so we are going to stop from here. And the next time, I'm going to talk this last part of this particular chapter, which is about the gravitational time delay of the signal passing the Sun. And this is also about Shapiro time delay. It is a small section. And after that, we will move on to talk about the behavior of the black hole. So that will be the next chapter. And that is in fact the second last chapter for you as well. And the last chapter, we will probably spend a considerable amount of time to look at the something called Friedman equation that is derived from a metric called Robertson-Walker metric. Right? So that is the real cosmology part here. Right. So I basically summarized what we have done in last 2 or 3 days. Anybody have any questions still? No questions. Right. So if not, let me stop today, and I will the next day of your class may not be the Monday. So I am not going to do the class tomorrow, by the way, right? So I have some work tomorrow, and